All right. All right, so last time we finished up our Rot13 thingamajiggy, and then we introduced this idea of shared memory. So we're looking at mechanisms to have two processes talk to each other. We're looking at shared memory first. The next thing we'll do probably, well, we might start talking about it today, but we'll do on Friday is an alternate approach to shared memory, and that is this thing called message passing. Just to give you a quick 50-second tour of shared memory versus message passing. We'll just do high level. Shared memory, multiple processes share a place in memory that they all know about. Message passing creates a direct communication channel between running processes. We can think of message passing as being somewhat of a wrapper around sockets / pipes. Really pipes for local communication, but you had previously looked into sockets and pipes and kind of what the difference between those are. We'll actually be looking at a message passing example next time, probably even almost doing the same thing as we did for today, but doing it through message passing rather than shared memory. But that's kind of the, we're looking at competitors here. So one thing we want to maybe keep our eyes on is the pros and cons of each. Why might we use one versus the other, and that kind of stuff. So these are kind of two different approaches of doing roughly the same thing. All right, so homework for today was to effectively integrate our two pieces of code back together. So last time we were looking at shared memory specifically, where we had our writer, we had our reader. So we have one guy that's going to write something to shared memory. And remember, the way we get our shared memory is we create a name for the thing, we create a token associated with that, which gives us a unique identifier. We printed out what that thing, this is just me printing out what the IP create, that it was some integer, some random integer, whatever. We use our shared memory get to actually get some shared memory with these permissions. What's this called when you have two things bitwise or together like this? Good. Masking. Okay, so we we can kind of create multiple permissions across each other through masking. So this is creating some shared memory that's going to be 1024 bytes or a kilobyte in size around this unique variable. So this is asking the operating system to get you a plot of land that can be shared around this key. The kicker here that some people had some issues with on the homework was the difference between shared memory does not dictate the kind of value you're putting in there. All right, so in this case, we talked about this a little bit last time, but this function here, shared memory attach, this says, so here's my shared memory ID. This is the unique identifier the operating system will, kind of like the phone number or the social security number of my shared memory, all right, associated with this guy. So I want to attach that shared memory ID to something else. And in this case, what I'm really doing is I'm getting a pointer to that shared memory that I can use inside my code. But what I'm doing is I'm attaching this guy, and ultimately I want to, the way I'm going to use it inside my program here is through a string. All right. So we're reading this in through a string. So I'm using it as a char pointer. So anything I do to this string will ultimately get saved in that shared memory location. So what's the real difference? What's the difference between using shared memory versus doing something like this? Me saying, char pointer str2 is equal to, we'll just say the char pointer version of malloc 1024 or something like that. What's the difference between these two lines? Well, first of all, maybe the thing is, what's similar between them? Go ahead. Yeah, both of these guys will ultimately be memory addresses, which point to the beginning of contiguous memory, right? str and str2 both hold memory addresses. Okay, so what's the difference between these two? Why don't we just use malloc here in this case? Isn't allocating memory allocating memory? Could two processes theoretically create their own shared memory using malloc? If a second process knew, if they were both in user space, let's say, and the other process knew the address of, maybe we write it out to a file or something like that, like, hey, here's my address. So you're gonna, you don't allocate memory. You just set your pointer equal to this dude because we're writing to the same place. We can effectively hack shared memory with that in mind, right? We don't maybe get some of the protections and stuff that we would get from the shared memory system, but both of these guys ultimately give us a memory address. This generates one directly. This, as he pointed out, will attach the memory that was captured here. So I guess this is technically where the address was created. It was generated here around this key. This attaches that shared memory address to our local variable. So locally in this program, our mechanism through which we access our shared memory is through this string, this char pointer. So I wanted to kind of clear that up, that shared memory does not dictate that we store strings there. Shared memory is a base address of a pointer. We can do whatever we want there, but the mechanism by which we reach our shared memory is going to be through a local variable that holds that pointer. Okay. So we'll go ahead and just start modifying this guy. So we'll do something like, enter we're going to say for right now, the word you wish to Rot13 encode. We'll read this guy in, and notice here we're scanning it into str. So let's talk about scanf a little bit more. We just introduced it last time and kind of said, hey, here's scanf, it just works. What's scanf actually doing? What does this guy actually accomplish? I'm describing here what I want to read in. So if I wanted to read in multiple strings or something like that, I could. But let's say I wanted to read in a string and then a number. I can say %s, %d, and then I could read this in, let's say I have an integer named I or something like that. I could do that type of thing, read multiple values into. So with that in mind, is actually doing parsing on its own, right? All right. We might say that modernly, this would be somewhat inconvenient, right? Because we saw last time that if you wanted to type in a sentence, it's only going to read the very first part of it, right? Why is that? Well, because scanf, we told I'm reading in a string, and a string terminates according to scanf based on the first space it hits, or the tokens you're reading in. Because scanf does its own built-in parsing, the tokens are separated by spaces. Does that make sense? You might be able to hack it actually if you put double quotes around it. But there are some more modern approaches to this where we can, there's a getS that allows you to get an entire string. There's also a putS that allows you to put a string someplace else. We could also implement our own version of scanf like thing around something called get C, which just reads in a single character, reads in a byte, a single byte. You just keep reading in bytes until you finally bump into the byte that is the carriage return, \n, something like that. That would allow us to read in a sentence. So just kind of, you know, we're not doing a whole lot of interactive type stuff here. If we wanted to have like a whole document and encode it into Rot13, maybe we wouldn't do this by having you type it in from the command line. Instead, you'd like write up a letter, save it in a file, read in that file, convert the whole thing to Rot13, and then maybe dump that to shared memory as an example. But for us right now, at least, we are using scanf. But now scanf, what this actually does is it's going to capture a string. Okay, now what's a string? A string is a series of characters terminated by a \0. And then it's going to get that into this string. Now, strings here are char pointers. So I'm using the generic, was there a question? Oh, I thought there was somebody online. We use the term string generically here, even though this is a collection of characters that behave like a string. That actually, let's go backwards. That we expect to behave as a string. Can I store a collection of characters that isn't a string? Is there a such thing as having, just like I could have an array of 10 integers, could I have just an array of 10 characters? And those guys don't necessarily have anything to do with them. They're not do with each other. They're not part of the spelling of a word. They're just 10 chars. I can store the alphabet, right? I could have a 26 bucket array of chars that holds the alphabet, and that doesn't spell a word necessarily. I don't use it as a string, or I don't have to use it as a string. So that is possible. So when I say char pointer here, really this is a character array as opposed to an int pointer, which is a int array. A string in our more modern approach, like with C++, we have a string class. Java, we have a very powerful string class. Those guys give us a level of abstraction that sits on top of a char pointer and says, the end user expects this to be a string. We're going to treat this guy as a string to make their lives easier. But in this case, we are dealing with character arrays that we intend to use as strings. And to accomplish that, let me get into it. To accomplish that, we have a library, strings.h, which we've seen a couple different times in some of our other coding examples, that allows us to do things with strings. Kind of common things here is like string copy. So string copy will copy a string from one location into a variable in another memory location. And all of these guys kind of follow that pattern where we pass in pointers to variables that we wish to fill up, as opposed to string copy returning a copy of a string, which is our more modern view of, like, if we were in Java and we wanted to create a new string that was a copy of an existing string, and we wrote a function called string copy, we would probably have that string copy function return a string, right? Whereas most of our functions in C return an integer, whether or not it worked or not. And instead, the return value is going to be filled into one of the values you passed in. All right, so string copy is a good one. String length tells us the length of the string. We wrote our own version of that, right? It just counted up characters until we got to the \0. The one that's going to help us the most here is, actually, it's not in here. It's going to be in IO, not IO stream. It's going to be in standard IO, Printf, right? Although string copy could actually, that we could make it work for string copy. In fact, let's do it with string copy, because I'm guessing most of you used sprintf. Okay, so sprintf says, here's a string, I want to print the contents of this string. That's the S part. S, we know what printf prints something to the screen. Sprintf prints something to a string. And what does it do? It does the magic of overwriting aspects of a char pointer, ultimately terminating it with the right \0. We could write it ourselves to accomplish that, right? String copy does something very similar, where we're taking in a source string. So this is the string we want to copy, and we're saying, I want to copy the contents of that string into this destination. In fact, as far as I know, depending on how it's written, actually, I was going to say, as far as I know, it's entirely possible that sprintf uses string copy, but it doesn't, because standard IO came out before string H. So I guess it's always possible they went back and re-implemented it, but probably not. It worked however it was. But we'll use string copy to pull this off. Well, actually, the one I'm looking at here actually returns a pointer to the end of the string rather than an int. There's a plain Jane string copy somewhere here. Or does it always give us the pointer? Let's see. The end of the resulting string at destination. Okay, yeah, so we're not going to use that pointer. So this guy does copy source into destination, but then it returns a pointer that points to the end of destination. The bucket right after. Actually, I wonder if it returns the position, the address of \0 in destination, or if it returns the position right after \0 in destination. One of those two, it'll be the end of the string. I suspect it'll be the position of \0. We also have string compares, things like that. Okay. So in any case, we're going to go ahead and we're going to read something in from our user, but rather than read it directly into our string here, I think you can string copy from the same string into another string. Well, really, we would be converting our code over here. Let's go into this guy. Let's just steal our functions. We really should probably write these inside of another file so that they both can use them, right? Because more than likely what I'm guessing most of you did is you probably copied all these functions into each of the two files, right? So you had your Rot13 conversion stuff. Yeah, that's what I'm saying. You can create a header file and import it from those. Although, what did you do? Did you import main.c? Okay, so let's look at that and then talk about why that's not the, let's say, preferred way of doing things. So you could have done include main.c, and that technically would get you everything that lives inside of main.c. But one issue you'd run into there is now you have two definitions of main. You dumped one of the definitions of main. Okay. So realistically, what you would probably do is we would probably say, we dump this guy like that, where now we have our prototypes and then you have your implementation, right? And then if we're doing this probably the way it should be done, we would rename this guy. Maybe call it Rot13.h. This is the header file that has our Rot13 stuff in it. All right, so now we have an encode Rot13, we have an index of, we have a string length, we have a code Rot13 string. So we have the functions that we might want to have available to us in both our writer and our reader, rather than copying the things into the two. All right, but so I would say that if you ever see somebody including a .c file, it's not that it didn't work, because I've said before, when you include something, all it's doing is replacing this line with the contents of that file. That's it. That's all it's doing. But typically you wouldn't import a C file, you'd import a header file, something like that. And nothing says that that header file needs to be, so we certainly could have had rot13.h and then also had rot13.c, which actually had the implementation in it. Right? So if we were kind of going down that path, we would have had let me just create another file in here, new file, rot13.c would be the implementation of the stuff from rot13.h. So we would actually take all of that stuff. So our header file would just look like that. And then in rot13.c, we would include rot13.h and then put the rest of our implementation in there. All right, with the argument being, hey, look, we want to separate our documentation from our implementation, fine, but if we include rot13.h inside of our writer, like that, and then let's just, for the time being, I'm going to comment out a lot of the shared memory stuff for a moment. Started it there. That should be right. Because these other closing ones that are in here. All right, and then what we'll do in here is we'll do something like char pointer s is equal to, what was the name of our function? Rot13, encode rot13 string. Something like that, and then we can do a printf %s, something like that. So we would do a writer.c, and if we just do that, it says that we have an undefined reference. So what do we actually need to compile? Writer.c and our rot13.c. Now it knows about that guy. All right. And this is where makefiles will then start coming into play, right? When you're having to start compiling a whole bunch of stuff together, what if we're just kind of moving towards like, hey, what does a real C library end up looking like? So now we have access to that function. Oop. So there's our hello in reverse or whatever. All right, so now we've given ourselves the ability of having both of our Rot13 things in both of our files without copying a whole bunch of code. Okay. Not wrong if you did it the other way, but certainly we would say this makes more sense. And if you wanted to throw all of your implementation stuff into your header file, it'll work. It's fine. But good programming practice would say to keep the things separate, even though I the reality is if you're not using a makefile, it's kind of more annoying to compile it and stuff. All right, so let's uncomment your uncomment these guys. All right, so rather than reading directly into our shared memory, what we'll go ahead and do is we're going to go ahead and we're going to say char pointer input is equal to the char pointer version of malloc. And if I was being reasonable about this, I probably would have done something like a dot define or pound define. Call this max mem. Isn't it define? How do I make macros? That's right, isn't it? Do a space who? Actually, I think it's this. No, no double quotes around it. So then we give the value. So we're saying define max mem to be 1024. So then we'll use max mem here, and we'll use max mem down here. And if we want to be explicit, we would say size of char. That's the number of bytes that we want to create is max mem times size of char. What does it like about this? Because that is a expected closing parentheses. Oh. Give me a second here. I'm certain that I'm doing something stupid. Well, here, let us do this. Oh. All right. So now we should be able to say times size of char. Just bad syntax. All right, so we're going to allocate some memory. How much memory? Maximum amount of memory, because, well, we know that's the maximum they'll fit in shared memory anyways, so we'll just kind of have those two match. But rather than hard code those values in there, we'll use a macro. So this is a good use of a macro. All right, then we'll ask them to enter something in. We'll read it in as a string, but we're going to go ahead and read it into input. All right, so now we have our string called input. Now we want to go ahead and convert this guy into, I'll steal that, into our Rot13 equivalent. So we'll say char pointer output is equal to that dude from input. And then we want to get output, which is going to be our Rot13 encoded string. We need to get that written into str. All right, have we already? We have not brought in string.h. And what was it? String pcopy? STP copy. STP copy. Source destination, okay. So we'll go ahead and do STP-CPY, and we're going to load it into string. And what do we, oh, hold on, sorry. Did I? Oh, thank you. There's Clancy. All right, so there's our output. So we're going to, our destination is string. Our input to that guy is our output string. This guy technically is returning a pointer to the end of str, but we don't need that. So I'm not going to capture it anywhere. So we'll just copy output into string, and then we will say data written in memory. We'll go ahead and just put in here, this is output. That's what we actually wrote. Actually, we could do S. That'll prove that our string copy worked fine. So I left it the way it originally was. I meant to put output here, but we'll leave it this way. All right, then we'll go ahead and detach from that string so that this local variable is no longer linked to our shared memory. And then this was a printf thing from before. All right, so let's go ahead and let's compile in writer. Come up here. So this is GCC writer.c rot13-.c, and then I might call my output writer like that. And what I'm going to do, certainly you can go and make, let's see, is it shift? Let's see. There you go. So certainly you can make a makefile for these things. But I would say kind of what I usually do is I'll do something like vi compile writer. I'll just put the code I want to have in there. Change mod on that. And now I have my compile writer. And that does will give me a file called writer. The -o is what my output file is called. So now if I do a /writer, enter the word you wish to compile. So it wrote that stuff into memory. Good. You could, because so his question is, can you use memcopy? Memcopy copies generic memory from one location into another location. Well, you mean for memcopy, how many bytes you're going to copy? You use str length. Yeah, so he's using something called MCP like that, right? So this copies a memory area. It's not saying this is a string or this is an int or this is generic memory that I'm copying from here to here. Just notice these, and this is related to things we've looked at before. We're saying, Here's a void pointer. That is an undefined pointer type. That's a memory address, the base address of something. So I'm copying the base address of something into the base address found here. And this is how many bytes I'm going to copy. And the reason string length worked is because it happens to be that strings are collections of chars, which are byte size. Make sense? But ultimately, in fact, it's entirely possible that STP copy is using memcopy under the hood. So this guy is a more generic way of copying one memory location into another memory location, not caring what kind of thing is stored at that memory location. So I guess I'd say, yes, you can, but it probably doesn't make that much sense in this case. It's not wrong. It's just, yeah, it's not wrong. It just feels like maybe a little bit of, yeah, I don't know. It's kind of the cool kid way, I guess. And readers should already be, we're not decompiling it or deconverting it, but we should at least be able to see this was the thing written to shared memory. All right, so we have that thing in shared memory. So now we want to go and do the same thing over in our reader. So we'll get our shared memory. We read in from shared memory, and this is the data we read. What we want to go ahead and do is we want to convert whatever's in str back into include rot13.h. Okay, I didn't put any extra special symbols or anything up there. Good, nailed it. And then we want to go ahead and convert this back. So we'll say char pointer, what is it in code, rot13 string, passing it str. And we'll call this guy, I don't know, answer, something like that. Do I already have an answer somewhere? Nope, that's good. And then we'll print out answer. All right, and then the reader. Now we have our two different compile things. So we'll do a compile reader. We'll go ahead and do writer again. And we'll do hello. So that's what was written. Then we'll do our reader. And this is the converted thing back to hello. All right, so that's using STP copy. If you wanted to do it, so a lot of you might be used fprintf or sprintf rather. Fprintf prints to a file. So if I come in here and I do man sprintf, here's sprintf, which lives in standard io.h. So this guy takes in a the char that we're printing to. Okay. So rather than the string copy here, which one, man, right? We'll go ahead and do sprintf. We're printing a string, but we need our destination first, right? Then the format. So this is going to go into, did I give myself string is my destination. So str, it's going to be a string and it's going to be coming from output. So we're going to, our destination will be printf. This is what this guy looks like, and output's the guy I'm writing. I think that's the right syntax, isn't it? Actually, we can probably cheat off of this as printf. Oh, actually, it looks like it's destination, source, and then format. Is that correct? That looks weird to me. Well, I guess we'll find out. All right, so we'll write to that. Similarly, we'll go over here to reader. Oh, we didn't actually have to do a thing over there. All right, so there's that guy. Then we'll look at reader, and that's what it read in. All right, so both of them ultimately will do the same thing. He mentioned he did a mem copy. So for your mem copy, you would have had to do the destination string, the source string, and then string length of the source string, because that's how much you were copying over. Yep. All right, so questions about that stuff. Go ahead. Yeah, so here, so you want to say, why can't you do this? Why can't you say str equals output? Yeah, where I have it's fine, right? Yeah, because we've already done the converting. Because so this is what you actually want to do. That's what you hope you could do, right? And that doesn't work, right? Okay, why doesn't this work? What is output? What's the actual value of output? A memory address. What is str capable of holding? What kind of thing is str built to hold? It's a pointer. Pointers hold what kind of value? Memory addresses, right? Now, the memory that we attach to is what shared memory gave us. So str holds the memory address of our shared memory. What did we do right here? We overwrote that memory address with a different memory address. Gave up our shared memory. It's floating around out there, right? Go ahead. So you want to say star str equals the value at output? That's a good question. I'm going to say no, because I don't think we'll test it, but I don't think strings are known dereferenceable outputs. Because actually, I'm positive it's no. What is star output? What is that value? No. Output's the memory address. What's star output? What value is found at, so output is the base address of our string. What value is found at that memory address? Very first character, right? Because we haven't taken any offsets from there. Because bucket 2 would be the base address plus 2 bytes, right? So this is saying, go ahead and set bucket 0 of that guy, the value. So this would write a little. we get one character moved over there. And then it would, yeah, so that's what that guy would do. Hence the reason why we have these helper functions like string copy and things like that, because a lot of, when you're dealing with this idea of base addresses and they don't dereference themselves, we now have to go through some sort of, we either have to write the code to say, okay, move this over, then this over, then this over, then this over, or use some pre-built tool that does move this over, move this over, move this over, which is making us kind of do a lot of swimming in memory. And it's not that it's difficult. It's that when you first look at it, there's a lot going on. You're like, you have to really force yourself to say, what kind of value am I dealing with here? Because we're so used to saying, oh, output's my string. It's the answer. It's memory address. We were lulled into this sense of overconfidence from like something like Java. It's like strings are objects, therefore they hold memory addresses. Yeah, but Java treats it like a primitive. No problem. How do I get the memory address of a string? Yeah, you can't. We'll take care of it for you. No problem. Now, how do we even get the value that's how do we get the value that's in that string? That's where we have to start using these placeholder things that say, look, treat this guy as a string. What does it mean to treat him as a string? Start at the base address and keep giving me stuff until you hit a \0. That's what it means for it to be a string, right? And if you've ever done, anybody in here ever done Objective-C programming? So in Objective-C, which is kind of an example, something I referenced a little earlier, and even in C, we have like, over the years, you've had evolutions of the string type. What we're looking at here is like the original string type, the char pointer that we just need to treat kind of a little special. Well, then we have something called C strings. C strings are a little bit friendlier strings, but they're not %S's, they're something else, right? In Objective-C, the string type is called NS string, next step string. It's an Apple library that was actually from Next Computers, yada, yada, yada. So the placeholder for that is a %, like that. That's a placeholder for an NS string. So just kind of interesting things that we've seen over the years as we take for granted more modern languages to say, hey, look, a string is a powerful thing. We all know what a string is. That's a string, no problem. Here's the string. Now we got memory all over the place. All right, so this dude's not going to work. I think this is this final version was something that did work, right? Just want to test it before I rate it. Yep. Okay. So what we'll do, what we'll do on Friday is we're going to look at effectively converting this over to message passing instead of using shared memory. How do we have these two programs talk directly to each other? All right, I will see everybody on Friday. Make sure you read on Slack. I think several of you already replied to it, but I am requiring that hackathon. Otherwise, there'll be an alternate assignment. But make sure you do that. Also, was it next week is the Tech Talk. I would look in general on Slack. V put it up there for Tech Talk from Komatsu Mining. Oh, it's right here. Go to that. It's on Zoom. I think it's going to be very informative. I met the guy. He's pretty sharp.